So this is half of this talk is based on my PhD, and the other half is just some thoughts on peak oil and gas, which weren't actually in the PhD, but which helped frame the discussion quite well. Just generally on peak oil, I tried quite hard throughout my PhD not to discuss it in too much detail until I had something interesting and relevant to say. And by the time there was something interesting to say, no one really cared about peak oil anymore, because since in the last year or so, peak oil as an idea has kind of really fallen off the policy scope. So that was a bit upsetting, but life goes on. So just a very brief outline. I'll talk about peak oil to some degree, give some background on it, and then kind of get into the body of the talk, which is looking more at, as well as resource uncertainty, which is a very uncertain thing, what other uncertainties are there which can affect how much oil and gas we'll produce for the next 50 years. So peak oil, it's the idea that we are about to reach a maximum level in production and decline thereafter, which is kind of the definition of peak oil, and that we'll reach a maximum level, has been recurrent for a huge number of years. And 1956, this paper by Hubbert was one of the first academic papers which we kind of really discussed it in detail and received a lot of press, but it had been discussed quite a long time previously to that. Whenever oil was first discovered in America, people were saying it was going to peak very soon and decline in the early 1900s. But the reason that the Hubbert paper is mentioned quite frequently is in 1956 he used a model which he developed himself, which I'll discuss in a bit more detail, to say that oil production in America was going to peak in 1970 and decline thereafter. And in 1970, that's what happened. So then everyone was like, wow, this model's amazing. What he's saying about global oil, which is the top graph there, when he said global oil is going to peak in 2000 and decline thereafter, might also be right, since he got America right. Not long after he published that, we actually oil production soared up to much higher than those levels, which he showed, and people kind of lost interest in it after about 1970, because we were at about, this is billions of barrels of oil per year, and he said it would peak at about 12, and we were up at about 20 odd. So people said, well, his model mustn't have been quite so good. But in the late 90s, this idea kind of came back again with Campbell and Laharère, who said, he used kind of quite a similar sort of model, and said, actually, although he got his numbers wrong, that model which he used was quite good, and let's do a similar sort of thing. And they said, well, it's going to peak in the early 2000s. We're currently at about, although it's not very nice to comment on other people's models, we're up at about 33 billion barrels. So, but we'll see why some of these things weren't so good at predicting things far into the future. And then since about 2005, there was a ramp up in the oil price. Steady ramp up, and more people got interested in peak oil, because they thought that this is a very simple way of explaining why the oil price is getting higher and higher up to 2008, before the recession hit. So more and more people got involved with it, and this idea kind of lived on till about 2012, when, as I said, people have lost interest in it again since. So I mean, it'll come back, I'm sure, in a not too distant future. The reason that people lost interest was because of the shale gas and tight oil, and they said that meant that peak oil was nonsense, even though they weren't. That's not really right. But anyway, so this is just to give 4 kind of broad outlooks of why there is some uncertainty in the amount of oil which we're going to produce. I generally look out to about 2050 or further, but this is out to 2030, and we can see there's an absolutely huge range in what people are saying. I've just picked 2. BP released an outlook every year, the IEA released an outlook every year, and these 2 every couple of years. And this is the latest outlooks, and this is what they say we were at and where we're going. So we've got from about 40 million barrels of oil per day up to about 100 million barrels of oil per day. So you've got an absolutely huge range. So that's why the outlooks of oil and gas are quite uncertain. Sorry, I should have said at the start, although this initial discussion is all about peak oil, you could just replace the word oil with gas, and it would be a similar sort of picture. So everything, all the kind of modelling and uncertainties that there are equally applicable to oil and to gas. The way this has kind of been discussed in literature is to say that these people are pessimists about the oil production prospects, and the people who say there's not going to be any sort of peak and is going to say it's going to keep continuing to increase or not peak are optimists. Now this is a bit of a artificial dichotomy, because there's actually a huge number of people who have outlooks which are somewhere in between those two ranges. So to say that there's just optimists and pessimists is a bit misleading, but it helps to frame the argument as well. So that's how I'll continue to talk about it. So there's a number of important aspects as to why you have such a large divergence between what some people say and what others say. And there were 4 things which I can identify which kind of help to explain why this was. The first one, which is kind of a bit of an academic discussion, is to say, well, actually, the way in which these two groups of people view oil or gas is completely different. So the pessimists are generally also geologists, and they say that the Earth is finite. Because the Earth's finite, we have a fixed stock of oil, and you can only produce that amount of oil. The optimists, on the other hand, who tend to be economists, say actually oil is more of an economic quantity, and if prices rise, the amount of oil is going to rise. So it's actually a much more fluid concept. And as a result of those two things, they feed into some of these other points lower on. The second point, which is incredibly important and is still leads to a large amount of misunderstanding, is that actually these two camps are talking about different things. The pessimists tend to talk about, I put in some quotes there, cheap oil or conventional oil or easily accessible oil, or some subset of what you consider to be all oil production globally, whereas the optimists would say, even if they think some sort of subset of all oil will peak, they'll say that total production of all types of oil, like oil sands in Canada, or extra heavy oil or tight oil or natural gas liquids, or lots of different types of oil, that will continue to rise, even though other individual bits which make up total production globally may peak. The next point is what's actually going to cause this peak. So the pessimists, and these 2 points probably best taken together, is how they model these things and what they think will cause the peak. And the pessimists tend to model it by saying, let's ignore the demand side and let's just focus purely on supply side dynamics. And they say that the supply side is a suitable proxy. So just looking at past production is a suitable proxy to model future production levels. And so you can say that any peak that will happen will be caused because we were not able to continue to increase production because of supply constraints. So peak oil is often framed as a supply constrained peak in global oil production. The optimists, on the other hand, the people who say there isn't going to be a peak, say actually you can't just look at the supply side, you have to look at the demand side as well. And actually historically, the optimists have tended just to look at the demand side and said, let's ignore how much oil there is and let's just say what's car demand going to be in China, and let's try and focus on modelling that, and that will tell us, and then there'll always be enough oil at some sort of price which will be able to match that demand. Recently the optimists have kind of also started to model the supply side in a bit more detail, but historically there's kind of been that a bit of a separation there. So it's worth just saying why do the pessimists, why do they think that it's okay to say that you can just look at supply side dynamics? And this is very much their view on how you can model these aspects, is to say, well, it's very well known, and everyone would agree that individual oil fields do reach a peak in production quite early on in their lives and then starts to decline. So we've got here an example from the UK, which is the Brent oil field, and after about 5-6 years of production, it reached a peak and it started to decline away, and that's purely driven by kind of geological aspects. Whenever you first drill a hole into the ground, the oil is highly pressurized and will come out of the well very quickly, but then that kind of natural pressure which is built up will start to die away, and as it does that, the amount of oil which comes out of the ground will start to decline. This dip is because there was an accident in the North Sea and they had to shut down lots of Piper Alpha disaster, and they had to shut down lots of rigs while they're doing safety checks. So that's kind of like a man-made decline. But broadly speaking, you can see that there's this decline in production over time. And they say, well, because of individual oil fields reach a peak, therefore you can say that individual countries will reach a peak, because a country is just a combination of all of these different fields. And so, for example, we've got in the UK, again, this disaster leading lots of things to rigs to shut down. But generally speaking, you can see that there's a bit of a peak and a subsequent decline. And that's driven by the fact that individual oil fields are declining. And then if you go up to the next level, you can see in the North Sea, so this is including of Norwegian production, similarly, it reaches a peak and declines away as well. And they say that you can just keep going through this kind of cascade of larger and larger regions until you eventually get up to the global level and say that, well, because regions peak, therefore global oil will peak. So just it's quite a simple method which they use to say, well, what oil production levels we're going to reach in the future. So just to explain it very briefly, what they do is they say what's historical production. So we've got here global oil production since 1850. How much oil do we think there is? And there's loads of different numbers you can use, and a combination of those two things will constrain what level you'll peak at and what date you'll peak at. And so what they do, by taking historical production and the total amount of oil, you can fit lots and lots of different production profiles. So this is, you can say, given past production, does a triangular function fit into this to fit past production well, and can that kind of the other side of the triangle explain what will happen globally, or is a Gaussian better, or there's loads of different distributions which are used. So these are using different symmetrical production profiles to say where is oil production going to go in the future. So just for a moment, since if we assume that this method is fine, one of the things that this method is fine to extrapolate or project where oil production is going to go. One of the big uncertainties, which is what's shown by these numbers, which is the kind of the area underneath each of these curves, is how much oil do we actually have, and what's the resource volumes that are available. And so this is kind of the beginning of what I started to look at in my PhD, which was what are all the different aspects which can affect how much oil we think it can be extracted. And I won't go through all of these, but generally speaking, there's lots of uncertainties. If you look at individual bits of oil, so if you say existing fields, nice kind of fluid oil, what sort of uncertainties can affect how much you think there is? There's issues to do with politics and economics and technology and geology, and then whenever you move on to more unconventional sources such as the Canadian oil sands, other uncertainties start to affect it. But generally speaking, there's quite a large range of uncertainty in all of these things, and that's why you get such a kind of a difference in how much oil is extractable. Just to mention one, which is the one which was really a large part of the focus of the discussion on peak oil, was the amount of reserves which was held by the Middle East. So the pessimists, the people who said that there was going to be a peak in oil production, said, well, we accept that this method of fitting production profiles to historical data is an acceptable method to project future production. So really what we're going to focus all our time on is this kind of the uncertainty in how much oil there is. And one of the biggest uncertainties they identified was what happened in the Middle East. So I'm sure many of you are aware of this. In the 80s, in the early 80s, a number of the OPEC countries decided to massively increase the amount of oil which they said they could extract, and this tied in, roughly speaking, with the time when OPEC production quotas became kind of proportional to the amount of oil reserves which you currently had. So people said that these kind of large jumps up in amount of oil which could be recovered, the amount of oil reserves, was purely a political decision. It was purely driven by the fact that they wanted to capture a greater share of the amount of OPEC production. So for example, it was Iraq was one of the early movers and said, well, we're going to increase the amount of oil quite dramatically. So they more or less kind of doubled it overnight, even though they didn't really declare there were any new discoveries or new or new technologies they'd used. They just said, we've got more oil than we thought we had previously. And then all the other countries said, well, if you're doing that, we're going to do that as well. So Saudi Arabia jumped up massively. And kind of supporting this discussion that these jumps were a political decision and not kind of driven by any sort of concept or idea of how much oil they actually had. A lot of these have been very, very steady since. So if you look at Saudi Arabia, for example, since this large jump up to about 270 billion barrels, they've just said we've got the same amount of oil every single year. So although Saudi Arabia's been the biggest oil producer since the 80s, they've never actually said they've used any of their oil. They've always just said, well, we've still got 270 billion barrels of oil, despite the fact that they produce kind of around 5 every year. So this lent support to the idea that this is political and this isn't the real amount of oil which they had. But this is an example of an uncertainty in resource availability. One of the other things I mentioned about this discussion on which leads to kind of this very wide range in the amount of in future production levels is that they disagree on what you consider to be oil, and I've kind of mentioned it already. You have two of the big classifications which happen are conventional oil and unconventional oil. This is a definition I use, which unfortunately no one else uses, which is to say that conventional oil is anything which is lighter than water. The industry standard way of measuring density is quite funny, and they use this thing called the API scale, but essentially 10 API, and also, sorry, it's the inverse of density. So as the numbers goes higher, you actually get less dense. But 10 is density of water, and anything higher than that will be less dense than water, anything lower than that will be more dense than water. And so I say anything which is lighter than water is conventional, and anything which isn't is an unconventional oil, and anything which you have to use, you can produce oil from coal and from gas and from biomass, that's unconventional liquids. And those kind of the three different classifications which you can use when you discuss oil. Just to mention, the IEA doesn't use that definition. It says that this new oil which is being produced from America, this light tight oil or this shale oil, is actually an unconventional oil, and they put it into that category. But generally speaking, if you look at the difference between these two, Colin Campbell is one of the people whose projection I showed, and he uses a very, very, very tight definition of what he defines conventional oil to be. He says it's anything which is heavier, sorry, anything which is lighter than 17.5 API, so slightly higher up on this density scale. And also, it's stuff which isn't in deep water, and it isn't anything which is in the Arctic regions. And it isn't natural gas liquids, which is oil, which whenever you produce some gas, you produce some oil with it, and those are natural gas liquids. He says that's not oil either, and he puts all of those things into the unconventional oil sense, and then says, well, this conventional oil is going to peak. So this production profile here, the yellow one, is his estimate of what's going to happen to just this conventional oil, this very tight definition of conventional oil. And that actually helps to explain quite a bit of this gap, because they're just talking about different things, which, although this is a very obvious and important thing which you think would be realized by everyone, it actually it hasn't been realized at all. And so people say, why are you producing a peak and you're not producing a peak? So, well, you're talking about different things. Also as part of my PhD, so I said I looked at all these different reasons for uncertainty, and as a result of that, I tried to put numbers on all of these things. So if you have a low estimate, a central estimate, and a high estimate for every one of these uncertainties which were identified, you can then start to build up an idea of how much oil you think there is and what the uncertainty in that value is. And this is kind of the culmination of that, which is you've got oil in the top and gas in the bottom, and it says that if you take all of these different types of sources of oil, you've got about 5 trillion barrels of oil, but the uncertainty in that is about 1.5 trillion either side. So just to give a bit of context, we've used since the beginning of time about 1 trillion so far. So there's an awful lot of oil which we can produce, but the uncertainty in that number is 50% larger than the amount of oil we've already produced. So the uncertainty is huge, even though the amount of oil we've got is huge. And just to give a bit more, these are the supply cost curves. So the amount of oil which is available at different costs, and to give but whenever you show the uncertainty like that, you can't see what different categories of oil are contributing to this this picture. So I've also split it out by existing reserves, reserve growth, the amount of oil which is undiscovered, the amount of this tight oil in America, the amount of natural gas liquids, and then the unconventional sources, which are Canadian bitumen, Venezuelan extra heavy oil, and oil shale or Keratin oil in America, which is different from tight oil. But there's a huge potential resource of Keratin oil. But the numbers which are attached to that are very uncertain, because there aren't currently any production techniques to produce this stuff. We just know there's lots of oil there which could be produced. So essentially the amount of oil you could get from that is from 0% to 100%, which means the uncertainty is huge, and that helps to explain a lot of the kind of the $1.5 trillion area of uncertainty. Just to mention gas, it's actually a very similar sort of picture. You have a central figure which is about 650 trillion cubic meters, and the uncertainty in that is again about 100 years of current production, or about the same as we've used since the beginning of time. So we've got an absolutely, again, you've got a very large range in the amount of gas which you think can be produced whenever you take into account all of these different uncertainties. So I'll come back to what that means shortly, but just to comment briefly, I mean, I said let's assume for the time being that this method of projecting future production was, let's assume that it's okay, this fitting production profiles to historical production, and actually it's not a particularly good method of projecting production at all, even though it's been used by a large number of groups and continues to be used. And there's a large number of reasons why it isn't a very good method of projecting future production. I won't go through all of them, but essentially it's got there's no basis, there's no reason why any sort of production profile should fit. You'd think there'd be some underpinning theory, but there isn't really. And also you can fit lots and lots of different curves to the same historical production data. So you can fit a triangular distribution or a Gaussian distribution, and they can both have very, very good fits to historical levels, but they're going to give you massively different levels of production which are going to come from that field or that region or that country or globally. So I mentioned that two procedures, so two different types of curve could both have an R-squared value of very, very high. You'd think that's amazing fit, but actually it's completely different, the amount of oil which they say will be produced in the future. So in summary, that it's not a very good method of projecting future production, but it does highlight that resource uncertainty is an important aspect to look at. But as well as resource uncertainty, there's a number of other features which may be just as important or may not be, and that's what I wanted to look at. And that's the title of this talk was Uncertainties in the Outlook. So I've just mentioned here two big aspects which could affect the amount of oil which you can produce. Top one is what cost you can get this oil out of the ground at. We have here an index on what's happened to capital costs since 2000, and basically since the early 2000s, the cost of producing oil has more than doubled. So this cost feature is a very uncertain number. There's also a very close correlation between this. This is showing the oil price in a given year versus the cost of producing a barrel of oil. There's a very close correlation between those two features. So we know the oil price has gone up significantly since 2000, and costs have actually tracked that very, very closely. So costs, generally speaking, are an uncertainty. Another big uncertainty is kind of your macro drivers of demand. So we have here, this is population projections, and this is GDP projections. This is looking at taking the numbers which are given by a number of different integrated assessment models, or the UN, or people who produce these long-term outlooks for where the population is going and where global GDP is going. And the grey range is kind of the total range from the highest to the lowest in both of these, and these are just some individual scenarios which which different groups use. So the blue one is the one I use, which is roughly in the middle of each of these kind of these fans of population and GDP. But I mean, we can see that this is, if you take population in 2010 to be just over 6 billion. Some people say it'll be the same in 2100, and some people say it'll be close to 14.5 billion. So I mean, you've got an absolutely massive range in the amount of population, and this is similar sort of kind of spread in GDP. But as well as these kind of two major areas, two other important areas is the assumptions you make on what your CO2 mitigation is going to be, which again is another aspect which seems to be overlooked a lot of the time with the peak oil discussion. So if you go for 5 degrees versus going for 2 degrees, those are two very different outlooks as to, or factors which could affect the amount of oil which you're going to produce. And similarly, technological development. Whenever we've got all of these unconventional sources from which no production currently occurs, it's very uncertain as to what levels they could rise up to in the future. You can use historical data to kind of try to help frame what levels these get up to and how quickly they get up to these high levels, but that's a very uncertain number. So it took, for example, the Canadians a best part of 50 years to get up to the level they're currently at, which is about 1.5 million barrels per day. But tight oil production in America has gone from 0 in 2005 to, I think it's up at about 3 or 4 million barrels per day in 6 years. So different technologies go up at very different rates, and that's therefore an uncertainty. I'm sure most of you have seen TM, don't need me to explain it. So what I did in the thesis was to construct a number of different scenarios. We looked at these different sensitivities. So there were 5 areas of uncertainty I was looking at, and these 5 major areas of uncertainty. And I did a central run, a high run, and a low run, which were for extreme but reasonable values of the high and the low for each of these different uncertainties I'm looking at, and a central run, which is kind of like the reference or case, which to it's not the central case isn't kind of my best estimate as to what's going to happen or the business as usual or anything like that. It's just kind of if you take a reasonable central value for each of the different scenarios you're going to run, what's your outlook look like. To explain very, very briefly what TM does is it models the entire energy system from beginning to end. So you have all of your fossil fuel production, which is the top line. You have all of your biomass and renewable and nuclear potential, which get converted into hydrogen or electricity. And then it has different demand sectors, and then there's certain demand levels which the model has to meet, and it meets them by supplying it with fossil fuels or with some of the other sources. And you can put various constraints on the model, such as a 2 degrees future, which will change what sources it used to meet those demands. And as part of the PhD, I did quite a few changes to how TM modelled fossil fuel production, just so it gave the outlooks it gave were a bit more reasonable. So I was tempted not to even bother putting up the central scenario because it's not really that relevant. Although people like to put numbers and all these sorts of things, actually that's not really the important part of the thesis, and it wasn't really an important part of this talk. But just to give some context to what sort of numbers it's producing, this is the central case, which is taking the central estimate for all of these different 5 levels of uncertainty. So it reaches about 3.5 degrees, I think. It takes the central estimate for where costs are going to go. It takes central estimate for technological development, and the central estimate for demand, and so on. So oil continues to go up, and gas goes up. Gas goes up much quicker, and you can use this to look at some of the individual. When I talked about the different subsets of oil, which they can be, such as conventional oil, this bit is kind of conventional oil, and so you can see it peaks within the model horizon, if that's what you're interested in, if you're interested in finding a peak. But actually all oil continues to increase up to 2050. Gas, on the other hand, continues to rise throughout, driven in large part by the levels of unconventional shale, tight and coal bed methane, which really rise in the future. But looking at the uncertainties in this central production, these graphs are the difference between these high estimates and these low estimates, and the central estimate I just showed. So the high CO2 is a 5 degrees future, and if you go for a high, it's oil and gas. So it's oil, gas, high, low, and If you take a 5 degrees future for oil, this is the difference in that outlook. So steadily over time, when you move from 3 degrees to 5 degrees, you use slightly more oil than you did in the reference case. But actually, you don't. It doesn't change particularly. It goes up by about 2050s. It's about 5 million barrels per day higher, and we were at about 120 million barrels per day. So it is. What it's saying is, if this is an uncertainty, but if you go from 3 degrees to 5 degrees, actually it doesn't make a huge difference to your production levels in the future. On the other hand, if you go from 3 degrees to 2 degrees, it makes quite a big difference. Just to explain this, I've split these bars up according to that graph I showed previously on my definitions, which is purple is conventional oil, brownie is unconventional oil, and green is biomass, is biofuels, and orange is coal to liquids and gas to liquids. These are the unconventional liquids. And so you can see that not only is there a kind of a 30 million barrel per day difference between the central CO2 and the low CO2, but also you've got quite a big change between the different types of oil which you produce. Gas is a bit different. Again, moving from the moving from the central CO2 to the high CO2 doesn't particularly change your outlook to any large degree. We are at 2050 there were about 6 trillion cubic meters, and it changes by 0.25. Or well, actually in 2050 it's not changed at all, so it doesn't particularly matter. So 3 degrees, difference between 3 degrees and 5 degrees isn't huge, but difference between 3 degrees and 2 degrees is much bigger. So this is saying that in early periods from 2010 up to 2030, you actually use more gas in your 2 degrees future than you used in your 3 degrees future, but in the longer term you use less. And this is, as a brief aside, this is kind of this idea that gas can be a bridging fuel to a low carbon energy system. That's what this is kind of suggesting, that kind of triangle between 2010 and 2030, that gas is useful in the short term to help you reach your 2 degrees, but in the long term it has to disappear away. I won't go through this in the same amount of detail, but this is just looking at cost uncertainty. I show that index as to where costs went from 2000 up to 2012, and they've roughly doubled since then. So I said, well, what happens if that goes back to what the costs were in 2000? That's your low costs. And what happens if they go up by the same amount again? That's what happens in your high costs. And that happens for oil or happens for gas. So if the costs for oil go up very high, this is the cost for the kind of the geological oil, the oil which is in the ground. You're going to use a lot less of those sources, but actually what happens is that you compensate for that by saying that you start to use more coal liquids and gas liquids and biomass. In the low cost, you use slightly more of your conventional sources and your unconventional sources, and that leads to about 10 million barrels per day. And I've just realised these are the wrong way around, by the way. That should be the low cost, and that should be the high cost. If your gas costs a lot more, gas is a much more fungible quantity than oil is. So if your cost for gas increase significantly, coal can step into the mix instead, and so that means that actually in 2050 you get quite a big effect if your costs increase. So it says the amount of gas you produce in 2050 goes down by 2 trillion cubic meters, so from 6 to 2. And similarly, if your costs are lower, it goes up by 1 trillion cubic meters. So what this is saying is that for gas is actually probably a bit more important than oil, because oil has other sources which can compensate for the amount of kind of production you've lost, whereas coal steps into the mix and you just use less gas overall. So I won't go through each of all the different 5 areas of uncertainty in too much detail, but this is kind of the summary of all of these aspects. This is what happens just looking at oil for the time being in 2030 and what happens in 2050. And it's not actually, you don't really need to look at 2030 too much, because all that happens is that the differences in 2050 extend the differences in 2030. So this is saying, if you just take in each of these, that's your difference in 2050, and then you take your net difference and put them all together, and compare which of these has the biggest effect on your global production levels. And actually, for oil, the biggest effects there are for the assumptions you make on your where carbon emissions are going to go, and assumptions you make on demand levels, on your kind of population GDP. And the reason that that's interesting is that, as I mentioned for the first half of this talk, all the focus of the peak oil discussion has been on resource availability, on those fan graphs that showed how much oil there is. And actually what this is saying is the amount of oil we have is a lot less important than a number of other features such as carbon dioxide or population. And it's about similar-ish to the assumptions you make on cost. So all of the technology isn't nearly as important, but of the other factors I looked at, your resource availability isn't as important as kind of historically the emphasis has been placed on it. Gas is actually a very different picture. Cost is the biggest thing, which affects how much gas you use in the future. By far and away, if you have your high cost estimates mean that you use a lot less, and your low cost estimates means you use a lot more. And then the next kind of biggest uncertainty is your resource assumptions, and the other factors matter a lot less. So saying that while CO2 and demand were the most important for oil, cost and availability are the most important for gas. So the areas to which they're most kind of sensitive vary between the two different types. And also it's interesting because the peak gas discussion is never reached quite as large levels as the peak oil discussion, because I don't know, people just weren't as interested in it, but actually maybe it would have been a better place to focus on to say this is going to affect your uncertainty levels. So just to conclude, a few very broad assumptions. The first one is that although you would have thought it would be fairly obvious, given it's not happened historically by a number of groups, you need to look at both supply and demand sides if you're going to model the outlooks for oil and gas. The resource availability is very important for these outlooks and what production levels are going to be out in the future, but that's only one uncertainty amongst many. And of the kind of the five major areas I looked at, they're different for oil and for gas, and resource availability isn't what's important for oil. Just very brief, just to say what does this mean for all of this mean for peak oil. I think although it's kind of completely dropped off the policy radar and what people discuss currently, I don't think that means that it was a wrong thing to be looking at. The original concept of what peak oil was discussing was a very useful and interesting idea. However, it then kind of got a bit waylaid and into a bit of a dogmatic discussion, which didn't really take into account the fact that conventional oil or a subset of all oil is what's important. You have to look at the whole thing, and you have to look at demand as well. And a lot of it, people who saw the kind of these peaks in production said, "Oh, we're running out of oil." That was never kind of really what the peak oil discussion was about. We're never going to run out. It was just we're going to reach a peak and decline thereafter. But as soon as people heard this idea, we're running out of oil, that meant as soon as there was a big new discovery of oil, people were like, "Oh, peak oil is dead." But that wasn't really what peak oil discussion was about. But as I say, it became a bit narrowly focused and slightly dogmatic, which it ignored a lot of the evidence, which didn't help things. And I'll finish there. Thanks. Any questions? Yep.
I was wondering, the situation for oil, if you'd expressed it as a percentage, it's quite a small change. The uncertainties were quite a small change. Is that what you're saying?
From these graphs?
Yeah, because if you're talking about 10, 20, 30,
yeah.
20 barrels a day, is that roughly what you're saying? That there's a small variability in the future.
Well, I mean, I think it's going from like a swing of 30 million barrels a day is quite large in the grand scheme of things.
That's about 30% or less.
Yeah.
But is there a higher sensitivity on who gets to use the oil, where the demand is globally? Because is that coming out of this analysis? It's a TM, but is there a region which is switching from, so you go from one end of the cost or the CO2 scenario, does it switch annex 1 to non-annex 1, that sort of thing?
In terms of production or in terms of consumption?
In terms of consumption.
I didn't look at it in a huge amount of detail, but I think it would be across the board. Generally speaking, if you go from 3 degrees to 2 degrees, you then start to move to kind of electrifying transport everywhere, because within TM, oil is it's very easy to trade, and very there's far fewer regional differences for oil than there is for gas. Gas is quite a different picture. So I don't think there'd be a huge regional kind of variation. You wouldn't see kind of like America going all electric cars and Africa staying oil based. They'd move in tandem. Gas would be different. Yep.
What about could you imagine modeling the geopolitical?
I did model that, but not using TM, because TM can't really do geopolitics particularly well. I mean, a geopolitical thing would be something like Saudi Arabia decides to stop producing oil. But within TM, because it's perfect foresight, they would know that was going to happen, and it would start mitigating it would start mitigating the fact that Saudi Arabia was going to stop producing oil in 2020, and basically probably stopped people consuming Saudi Arabian oil beforehand. So it doesn't really work in quite the same way. That's the reason I used the other oil model, was to look at geopolitics. This TM was designed to look at the major kind of overarching long-term trends, whereas the oil model was to look at kind of the specific geopolitics on these uncertainties.
Are there any of these uncertainties that you think we can control or learn about? And if so, to what extent? And what effect does that have on what are your forecasts?
Well, I mean, you could, for example, say you can control the CO2 levels by, in theory, given there's an agreement to stay to 2 degrees, that shouldn't really be an uncertainty, but it's more an uncertainty because we think it's uncertain. So it has been controlled to some extent, but it's just looking so unlikely that people have neglected it. I think it'd be quite hard to control it. Like, you can't really control the amount of. It's hard to know now, kind of, if you look at resource availability, how much oil you're going to be able to produce using a certain technology, or whether a certain technology is going to become available. And I don't think you can really narrow that down to any greater extent. It's just kind of something you have to bear in mind and take account of. I can't think of any that you could really control. Yep.
On the question of availability, we focused on looking at production, demand incentives, or is it just a case of production?
I think that kind of demand was completely ignored. It was just, so you just looked at production profiles from individual countries, and either individual regions or from individual countries, and said this country is going to produce kind of 10 million barrels of oil a day because it produced 5 million yesterday, and kind of demand or consumption or all that just didn't really enter the discussion at all.
So do you look into that?
Yeah, so TM has the kind of the energy service demand, so billion vehicle kilometers, tons of shipping, whatever, and that it has a demand which the model has to satisfy, and it has to find a way of satisfying that within all the constraints you place on it, and that will be done on a regional basis. Yeah.
I was wondering, you showed the cumulative graph of oil availability.
Yep.
Do you know where I could find these graphs for future scenarios, such as like P2032?
Well, I mean, that's one of the things about these things. Is this is supposed to be over all time. So this is the total amount of oil which you have available now, and which you could produce till the end of time. The fractions of that which you could produce up to 2030 are very subjective, and it's very hard to produce a supply cost curve in the future based on what's happened in the past, because you don't. Say for example you wanted a supply cost curve in 2030, and how would that be different from what happened in 2010. It would depend on what you did between those kind of two periods as to whether you could reduce the supply cost curve. And people don't really seem to do that. The IEA did it in its last World Energy Outlook for the differences between its scenarios into what the supply cost curve looked like. But generally speaking, it doesn't really change a huge amount because the amount of oil we have available is so large that the curves don't shift a huge amount. But the IEA's got quite a good...
But I'm wondering about this, whether there are any issues that are worth looking at about maybe changing cost for each of these types of oil. Because if one column gets significantly lower, then we...
people don't really tend to do that. I mean, you can do that with all this data if you wanted to, but I don't think others have really done it to a huge extent. I don't think so. You can have some of my data if you want. All right.
For your cost and price graph correlation was quite compelling, but that seems something that people are.
Yeah,
You found that quite contentious.
Yeah, economists don't like that at all. The basic economic argument being that cost drives price, but it doesn't describe causation between price driving cost, but there are some quite good mechanisms as to why price could be driving the cost. So, for example, in Canadian oil sands, as the price goes up, driven by an exogenous factor, let's say some sanctions happen in Iran, price goes up. Canadians say, well, this oil is now economic, but because it's in the middle of nowhere, we can't get anyone to work there, so we have to start paying them more. And all of the service companies start charging more because they can start charging more, so the costs start to go up as well. So there are some mechanisms by which price can start to affect the costs, but also costs would affect the prices, and it's kind of quite a... but economists kind of completely disagree because it's heretical to the economics.
Are you talking about marginal cost? So that's the cost of an additional unit of production coming online, the average cost, because presumably if you've still got large amounts of oil being produced in Saudi Arabia at $10 a barrel, it's the shipments coming online or something.
That is marginal cost, but if you look at average cost, it would be even more compelling because as the price goes up, you would assume that you would bring on more high cost oil as a result, which would drive up your average costs as well.
I guess it depends what volume you're going from Saudi Arabia.
Well, yeah, but I mean, no matter what volume you bring on,